Welcome to Chemistry 112. Today we'll be going through last year's test. This should hopefully at least give you an idea of the types of problems. Though keep in mind this last year's test was a take-home exam, so it's guaranteed to be a little bit harder than what I'm planning, especially considering all the questions you had to look up your values. So I have the tables all pulled up, so we'll look into those as we need to. But for the most part, there's only set amount of different reactions. Keep in mind this probably does not include, if I remember right, this does not include our nuclear chemistry, but the nuclear chemistry is not meant to be hard. So I might make up a problem on the spot and we'll see where that takes us in the end. But okay. So a quick reminder, this take-home test, I asked them to use their book or online source to get all values of H, S, G, and E, and to state the source of their values. On the test, if you need the delta H or delta S or delta G, they will be in a table right adjacent to the problem. If you need the E cell values, they will be on the last page of the test, along with the periodic table and the useful information sheet. Keep in mind, you can have one-page cheat sheet, front and back, handwritten. But no, you don't need any delta H values, you don't need any delta S values, you don't need any E cell values. What I'd suggest is maybe showing yourself how to work out certain problems, a reminder of how to set up a K expression, or how to balance a chemical reaction. Because some of those things, it works best if you can actually do it. Okay, starting right off, we have a four-part question. Iron, essentially, it's the corrosion of iron, where we have magnetite goes to hematite, iron 2,3 goes to iron 3 in the presence of oxygen and acid. The first step, I'm asking you to balance this and then determine Gibbs at 25, cell potential, and equilibrium constant. So the first step is to balance this. Now, okay. Go to DocCam. To balance this, we're going to split it into the two half reactions that's already there. We need to, I don't know why I'm rewriting it, but we need to first balance the non-hydrogen, non-oxygen elements. So from there's 3 irons, there's 2 irons. I have to do the greatest common factor between there. So the greatest common factor would be 6. So if I put a 3 iron 2 iron 3 oxide and a 2 iron 2 3 oxide, that will balance that. There is no non-hydrogen, non-oxygen elements there. So I don't need to worry about that. I'm going to go ahead and finish off this equation before I work on the next one. So next, there's no hydrogens, but we're going to do oxygen next. So there's 2 times 4, so 8 oxygens there. 3 times 3, 9 oxygens there. So what I have to do is I have to put a water on the left. So now that we have 1 plus 2 times 4, or 9 oxygens. 9 oxygens. But by adding that water, I have disturbed the equilibrium of hydrogens. So now there's 2 hydrogens on the left and 0 hydrogens on the right. So I'm going to add 2 hydrogens on the right. The last step is we add the electrons. As I said, you might have to consider the oxidation states if you do it any other method but mine. My method wants me here, what is the total charge on the left? 0 and 0, the total charge is 0. The charge on the right is 0 and 2 plus, So the charge on the right is 2 plus. We have to make the left charge and the right charge to be the same. Since we're adding electrons, it can only ever go down. We can never go up. So I have to add 2 electrons to the right. 2 electrons to the right. Which you might have to figure out the charge. Oh, this is actually made up of FeO and Fe2O3. And there's so 2 of those and 2 of those. This is going from 2 plus to 3 plus. What's doing it twice? So it's losing 1 electron per magnetite. But you don't have to consider this in this method. You only have to balance the pluses and minuses on each side. So let's do this guy. H plus O2 goes to H2O. So first thing first, we balance the oxygens. 2 oxygens, 1 oxygen. 2 oxygens, 1 oxygen. What do I got to do? I have to double the water. Now it's 2 oxygens, 2 oxygens. Now 4 hydrogens. So I need to make this 4 hydrogens. Oh, that's good. Now we have to add electrons. 4 plus 0. So I have to add 4 electrons here. Now when it comes to adding this reaction to this reaction, I have to balance the 4 electrons with the 2 electrons. Because we need 4 electrons gained, 4 electrons lost. So I have to take this whole thing times 2. That means we're going to have 2 waters, 4 magnetites, goes to 6 hematites, and 4 hydrogens and 4 electrons. Now when I add these guys together, this guy's going to cancel here, left and right. This guy's going to cancel here, left and right. And this guy's going to cancel here, left and right. So when I add these two together, it becomes, last but not least, 4 Fe3O4 plus O2 goes to 6 Fe2O3. So 12 irons, 12 irons. That's 16 plus 2, 18 oxygens. 6 times 3, 18 oxygens. The equation is balanced. Now, this is a solid, this is a gas, this is a solid. Now, if we're trying to balance this via, the next step is to find the Gibbs free energy. Now, there's 2 ways you can do this. You can find it via delta G equals delta H minus T delta S, where you have to find this value and times 298. But because we are given the option, and this is delta G at 298, we can just look up the delta G values. We can look it up on the table. We can just look them up directly from the table and find what we need. So the hard part is just finding our things. So I got to scroll down. This is alphabetically by element. Oh, just a quick reminder. The first column is delta H, second column is delta G, third column is delta S. So as long as we just need G, we just have to look at the second column. However, if we were trying to find delta H, we'd have to use both the first and the last column. So here's our iron. Fe2O3 is negative 742.2. I'm going to write that down on my paper, 742.2. Once again, on the test, you would be given this. Fe3O4 is negative 1015.4. 1015.4. Now I just need to find oxygen real quick. Oxygen. O2. Notice the delta H of O2 is 0. The delta G of O2 is 0. How much Gibbs free energy does it take to form oxygen from oxygen? 0, because oxygen is how it normally appears. Oxygen is how it's normally found in nature. Okay, so to find our delta G is our sum of delta G of the products minus the sum of delta G reactants. Our final minus initial. So products, negative 742.2 times 6, because there's 6 iron oxides, minus negative 1015.4 times 4 plus 0. Doing the math. 32.6. 742.2 times 6 is, go down so we have big number, negative 4453.2. And the other one, 1015.4 times 4 minus a negative 4061.6. So our delta G value is equal to negative 391.6 kilojoules. 391.6 kilojoules. So that answers A and B, 391.6 kilojoules. I'll write that down on the next page. Delta G is, because we'll be using that, I have 391.6 kilojoules. Now, the second step asks us to determine the cell potential. Now, there's two ways you could try to determine the cell potential. You could try to find the half reaction on the cell potential table for the first one and the half reaction of the cell potential for the second one. You might have an easy time actually finding this guy, the second, where is it? You might have an easy time finding this one, but you may have a really difficult time finding that one. So what I suggested, and I gave you a hint, you can use Gibbs free energy. You can use Gibbs free energy to determine this. So we can use this two different ways. Remember, our equation is delta G standard equals negative NFE standard. So if I have a delta G, I can solve for E. If I have an E, I can find delta G. So if there's ever a question where I'm asking you to find Gibbs and you're not given an H, S, or G value, know that you can get it through this equation. So rearranging this, you can say that E is equal to negative delta G over NF. The only thing we need to remember from that last page was that N, the number of electrons, was 4 electrons. 4 electrons lost, 4 electrons gained. And that kilojoules needs to be turned into joules. So rewriting the equation, negative 391.6 kilojoules times, there's 1,000 joules in 1 kilojoule, divided by 4 times Faraday's constant, 96485. That's essentially joules per mole, joule volts per mole. Well, actually, joule per mole volt. So this will give me units of volts. Now, don't worry about memorizing that number. That number will be given to you. However, some graphing calculators will actually have that number somewhere on it. So 391 becomes 391,600. We divide that by 4, divide that by 96485. You get the voltage for this guy is a positive 1.0, we'll say 15 volts. Probably don't need to use that many significant figures, but I mean, that's 4 significant figures. I'll keep it with 4. But so that's our voltage. That answers question C. The last part here, question D, determine the equilibrium constant at 25 degrees. Once again, you can use your delta G for this, or you could use your E cell for this. It doesn't matter. Delta G, so the other equation is delta G equals negative RT ln K. The delta G E cell RT ln K. Once again, we have to watch out for units, but you can rearrange this to say K is equal to E raised to the negative delta G over RT. And T is 298 because it's done at 25 degrees. So rearranging this, I'm going to start by finding delta G over RT. So negative 391.6 times what, 1,000 joules and 1 kilojoule divided by 8.314 times 298 equals ln K. So let's first find out what ln K is. 8.314 divided by 298. So ln K is equal to 158. We'll say 06. Now, the inverse log, so K is going to be equal to e to the 158.06, which is a very big number. 441 times 10 to the 68th power. Very big number. But what would the K expression actually look like? Remember, it's products over reactants raised to the power of their coefficients, but we don't include solids, we don't include liquids, we just include gases and aqueous. So what is the only thing that would be included? O2. Our K expression would actually be 1 over O2. So at equilibrium, when the reaction stops, you would have, the only time this would really stop is when either the iron runs out or you have like microscopic quantities of oxygen. This would be, let's see, if that's, let's just calculate molarity. If that's in 1 liter, if that's in 1 liter volume, let's see, grams, no, 6.0. Yeah, it's almost too small to like fathom. Yeah, it's too small to fathom. It really is. We're talking about below atomic levels. This reaction, if there's acid and if there's oxygen, And if there's hematite, magnetite, it will go. K is very big, which is why iron will rust under the right conditions. So that's the first 4 questions right there. As I said, don't expect to have to look up these values. They will be either on the table or on the back sheet. So next one, the dissolution of silver chloride to answer the following question. So writing this equation, AgClS goes to Ag plus and aqueous and CO minus. So first I asked to determine Gibbs at 25. And then I ask, is there a temperature where this is no longer, where the sign of Gibbs will change? So in this case, it would actually behoove us to, and then find the entropy of the universe at -12 and the Gibbs at 150. In this case, it really does behoove, oh, and finally, find the K at 150. It really does behoove us to find the delta H and the delta S values rather than simply looking up our delta G, because the delta G values will give us the first answer correctly, but the delta G value by itself will not give us B, and you will not get C correctly, and you will not get D correctly, because the equation is delta G equals delta H minus T delta S. Okay. So I'm going to pull up the document and we'll look it up. Look up our values. So going back to, oh, I got to pull that up over here. Okay. We're going to find, we'll find silver first. Silver alphabetically by S. Silver plus, I'm going to write down my delta H values and on my delta S values rather than worry about any of the delta T. So remember, delta H is the first column. So delta H for Ag1 plus is 105.579. Delta S value for that is 72.68. AgCl solid is negative 127.068, and S is 96.2. Now, the last thing I need to do is go back to chloride. So we go back up. It's alphabetically by the name, not the elemental symbol. Chlorine. So we have chlorine is either chlorine gas or chloride. Chloride is negative 167.159 and the 56.5. Okay, we got all we need from this table. We can go back and start working out our actual numbers. Remember, delta H is products minus reactants. The sum of all products minus the sum of all reactants. This will not change. This will not change between all 1, 2, 3, 4, 5 problems. So doing this number once will give us a good value. Products minus reactants. Everything is 1 mole, so we don't have to multiply anything by a coefficient. So 105.579 and negative 167.159 is negative 61.58 minus a negative 127.068. So our delta H is positive 65.488 kilojoules. Our delta S, same process. Products minus reactants. 72.68 plus 56.5 minus 96.2. So the products, when you sum them up, are 129.18 minus 96.2. The delta S is 32.98 joules per mole Kelvin. If this is kilojoules per mole, that's joules per mole Kelvin. Now we have all the values we need to answer the first three problems, because we got delta G minus is equal to delta H minus T delta S. So the first question asks us, what is delta G at 25? That's going to be 65.488 kilojoules minus 25 degrees is 298 Kelvin times 32.98 joules per mole, or joules per Kelvin. So what do we have to do? We have to turn joules into kilojoules. Always have to remember that. Otherwise, this side will blow that side out of the water. So 298 times 32.98, but divided by 1,000 is essentially 9.8. This whole thing is 9.828. So 65.488 minus 9.828 equals 55.66 kilojoules. What does this tell us about silver chloride dissolving? It is not spontaneous. It is not spontaneous. What do we know about silver chloride? From everything I've shown you, Gen Chem 1 and Gen Chem 2, is that silver chloride will naturally precipitate. Silver chloride solid is the standard form of what happens when silver and chloride are together in solution. They form a solid. So what is the likelihood of this unforming and breaking apart? It is pretty low. Positive delta G means it's not spontaneous. Now the next step, question 2, what is the temperature at which this might change? The temperature is going to be delta H over delta S. Once again, watching the units. Delta H minus delta S. So delta H is, as I said, 65.488, and this is kilojoules. So what do we have to do? We have to say there's 1,000 joules in 1 kilojoule, all divided by 32.98 joules per Kelvin. So when we take 65.488 and divide it by 32.98, what temperature would this become spontaneous? It'd be 1985. Well, let's say 1986 Kelvin. 1986 Kelvin. That's pretty high temperature, but it basically, what's one fact of the matter? What's one fact of the matter? Solubility of solids usually increases with temperature. On something that is really poorly soluble, you have to increase the temperature by a lot. And of course, in this case, water would have long since boiled. Okay. Now, the last three problems, I'm going to rewrite the numbers. 65.488 65.488 is our delta H, and our delta S is 32.98. Negative 12, 150. Okay. Sorry. So the next question asks for Gibbs free energy. Not Gibbs free energy, but entropy of the universe. Entropy of the universe is simply entropy of the universe is delta S minus delta H over T. Because essentially you're figuring out the delta S of the system plus delta S of the surroundings. The delta S of the surroundings is this term. Once again, units are important. Units are important. So as we do this, 32.98 joules per Kelvin minus 65.488, that's kilojoules. So what do we have to do? 1,000 joules and 1 kilojoule divided by our temperature. Our temperature is negative 12. So negative 12 plus 273 is equal to 261. 261. 261. So what this gives us is joules per Kelvin there. So that term, 65488 divided by 261 is negative 250.91. When we add those together, you get the delta S of the universe is negative 1217.93 joules per mole Kelvin. So that's the answer to the second step, the third question. What is the delta S of the universe at this temperature? What it comes down to is just a rearrangement of our Gibbs equation. It's just a rearrangement of our Gibbs equation. Is all it was. So, finally, last two products. What is our delta G if it was at 150? Delta G at 150 would be our 65.488 minus 150 plus 273 is what, like 423. So 423 times 32.98. If that's joules per mole Kelvin, we have to then go in 1 kilojoule, there's 1,000 joules. So 423 so that whole term goes to 13.95. So 65.488 minus 13.95 is 51.538 kilojoules. So the Gibbs free energy has changed. At 25, it was, at 25, our answer was 55.6. At 150, it's 51.5. So it's dropped by a little bit, closer to 0. The last question, what is our K at 150? So remember, delta G equals negative RT ln K. At 150, so we have 51.538 times there's 1,000 joules and 1 kilojoule divided by 8.314 and 423. First, I'm determining what is ln of K, just to be like showing all of the steps. So you're not like, if you screw something up one place, you know where you screwed it up. So this is negative 14.65 equals ln of K. So the inverse log of that is going to be, so K is going to be 4.32 times 2. 4, 6, 10 to the negative 7th. Considering the fact that I think it's normally something like along terms of 10 to the negative 10th, that's something 10 to the negative 7th is a significant improvement. So the solubility of silver has gone up, but is it spontaneous? Answer still no. Okay, going back to the Word document. So that answers those 4 questions. Now, don't expect to, or 5 questions. Don't expect to have to do this one again, but the question is, in your own words, restate the second law of thermodynamics and why it's important. It's the idea that for a spontaneous reaction, the entropy of the universe always increases. What that means for us is that the idea is that nothing can happen without some sort of outside work. We can't force anything to happen without any outside energy. It's like if I want to push a ball back up a hill, you have to put work into it. If I want to, say, decrease the entropy in this little area, I have to put energy into it to make that happen. This is the whole reason why there is no such thing as a perpetual motion machine. The idea that in order to stay in motion, there has to be some sort of outside force that's going to give it the energy to make it run. And that's what makes it so difficult. But, okay. Following lead acid battery. Use it as the following cell. So we have lead. I'm going to write these down. We have lead oxide goes to lead sulfate in the presence of sulfuric acid, H2SO4. And H2SO4 will reduce lead to lead sulfate. So the reaction moving left to right. You move left to the right, you can look at the reaction as a direct conversion. So first, determine the E cell, and second is a question involving the output. But second one doesn't actually have to, you don't have to do the correct one right now to do it. So we're going to jump to the achieve, not the achieve, but the thing so we can look this up. So, well, actually, I'm going to go to the doc cam first so that we can understand what's going on. The idea is 1/2 reaction with some amount of acid is going from lead to lead sulfate. That's 1/2 reaction. Because reading left to right, this goes to there. The other reaction is going lead neutral, lead solid to lead sulfate. Because reading left to right, going there to there. So we're going to look for those 2 half reactions on our document. Okay. We need here's the first time we're actually using this table. All these are written as reductions. There's PbSO4 goes to Pb solid. Now right there is the opposite of what we want. For the right column, the opposite. So 0.3588. They've either changed it or I expected them to use the one in the different table, but we'll go ahead and use one of these. 1.460. It's not quite what I was looking for, but without spending more time, I will say 1.460. Now, I'm sure they have one in the on the table in our book, but we're not going to worry about that right now. So we have on here, we've written down our values. Lead oxide goes to lead 2 plus, and lead goes to lead sulfate. Now in here, the left one appears as written. We keep that the same. The right one is opposite as written. We minus it. So our voltage would be 1.460 minus a negative 0.3588. Because this value is for the reaction going that direction, opposite of how we have it. So our total voltage is 188 volts, or something thereabout. Once again, your numbers may vary depending on what your sources are, but that will work. Products you have to be able to read the battery notation, but notice your left to right. This is your reduction. This is your oxidation. It's the E reduction minus the E oxidation, anode minus cathode. What is the cell potential? High output alternator of the Kia Soul can produce 220 amps current. How long would it take to recharge 4.03 kilograms of lead, assuming your battery is near dead? All this is going from lead to lead 2 plus, so there's going to be a 2 electron change. So the dot cam. The equation is mass equals charge times time times molar mass over NF. We have a mass, we have a coulomb, we have a current, we have the N. The N is the only thing we have to really think about. It's the 2, and we need to find what is the molar mass of lead. I think the molar mass of lead is something like 207, but we'll double check that before we get any further. Lead Pb is 207.2. Mass is 207.2. I will give you this equation on the test, so you don't have to memorize it. However, writing down how to use it is not a bad idea. 4.03 kilograms. We need this in grams. So that is 4,030 grams equals our 220 T times 207.2 over 2 and 96485. A little bit off there. So 4,030 times 2 times 96485. Okay. Going to be a big number. Divided by 207.2 and divided by 220. Our time units, after we do that, our time units are equal to 17060 seconds, because current is always amps, is always coulombs per second. So if I wanted to turn this into something more useful, maybe divided by 60. That'd be 284 minutes. Or divided by 60 again, 4.7374 hours. That's how long it would take to fully charge the battery going at max current if we completely killed the battery. So expect at least one problem with charging, or either calculating the time or calculating a mass. It's not supposed to be too hard, but it is kind of a weird equation. A non-spontaneous electrochemical reaction. The reaction with the highest voltage, lowest negative voltage will predominate. So if you have a solution containing only sodium, chlorine, H plus, OH minus, and water, and I connect it to a 1.3 volt amp, what reaction will occur? So this one is a tricky one. It is one that you actually have to think about really hard. But then again, it was a gosh darn take-home test, so I don't expect everything to be super easy. So what you had to do is look at the half reactions that were possible. Half reactions were possible. Let's look at sodium. Sodium, the only one possible is Na plus. Well, one electron goes to Na solid. Okay? A negative 2.71. Now, please note, you cannot go from Na solid to Na plus. We cannot have that half reaction. You want to know why? We don't have Na solid. We only have sodium plus. So we can't do that one. Chloride. We only have Cl minus. We can only do this half reaction of 1.3 of, so we can only do this one. We are given Cl2 goes to plus 2 electrons, goes to 2 Cl minus, 1.36 volts, but we can only go that way. We can only go from right to left because we only have Cl minus. We only have Cl minus. Now, when it comes to H plus, let's see if we have. So the big one is H plus, 2H plus, and 2 electrons goes to hydrogen gas at 0 volts. That's the only one we can really do with H plus. And then let's see, OH minus. Oh, there we go. H2O. Right there, we'll use that one. H2O can split to form H2 and OH minus, 2OH minus, at negative 0.8277. And we could have this one, O2 plus 2 waters plus 4 electrons goes to 4 OH minus. But we could only have this in reverse. We can only have this in reverse because we, once again, do not have oxygen. We don't have oxygen. Okay, I think we're almost. Yeah, we're back to the top. Okay. So this one really, really is a head scratcher in that. So I got to move this here. We have, flip that around. That would be negative 1.36 volts. we have to have a mixture of, I'm going to write this down into two columns. Na plus, 1 electron. We could have H plus and 2 electrons. That's negative 2.71 and 0 volts. And we have water, 2 electrons. And that's negative 0.8277. The other one is 4OH minus at negative 0.401 and Cl minus at negative 1.36 volts. So notice I flipped the sign. I flipped the sign when I flipped the reaction around. I flipped the sign. So we have to have an oxidation. We have to have a reduction and an oxidation. And we're going to choose the combination that has the lowest potential, the lowest negative number. When I add these numbers together, which one has the lowest negative number? Would be this guy and this guy. If I add them together, what are we going to have? We're going to have 2H plus 2 electrons goes to H2. And you have to double it, so 4, 4, and 2. And then you'll have 4OH minus goes to 4 electrons, 2 waters, and oxygen. When we add this together, what do we have? Essentially, 4 H's and 4 OH's makes 4 waters. You get essentially the reaction of 2 waters split into 2 hydrogens and oxygen at a voltage of negative 0.401 volts. This is what happens in certain overcharging situations. That instead of getting the recharge that you want, you get this recharge, and you start producing hydrogen and oxygen in the battery. What do we know about hydrogen and oxygen together? Well, hopefully you know flammable. You get a loose spark, you get a big boom. That's why certain batteries will explode if you overcharge them, because you're producing hydrogen and oxygen on the terminals, a spark, and then suddenly your battery explodes. Most batteries have a degassing valve, a valve where they can release that built up hydrogen and oxygen so that it'll be formed in trace amounts over time. But if you go too much too quickly, it builds up and you have an explosion. This one is, we don't have to worry about that one. That one is well beyond what we need to do. But the whole idea there is, it was a tricky one, meant to the people who really could do it would get more points, and that way I could separate those who could not do it. Okay, combustion of ethanol. Determine the enthalpy of the reaction. Without calculating, what would the entropy be? So C2H5OH liquid plus 3 oxygen and goes to 2 CO2 gas and 3 water vapors. I can see, and then so find the delta H. Then it says predict the S, and then that's all that one is. So I'm going to do B without really even looking at it. So the question is, what is entropy without calculating? Would you expect it positive or negative? So the change in entropy, the idea is that entropy is related to phase and number. There's 5 molecules of gas on the right. There's 3 molecules of gas on the left and 1 molecule of liquid. So just looking at that, 5 is greater than 3, entropy should increase. The randomness should increase because there's more gas molecules. I can completely ignore the liquid there. Can completely ignore the liquid there. But so when we go to solve that one, I'm going to pull up the document. I'll go back to so yeah, what do we have for carbon? Carbon has a separate one. No, okay, here's carbon. Carbon, we have, I'm guessing they have a whole separate thing for this guys. O2, I can tell you right now, is 0. What we need, the only thing we need right here is CO2 gas. CO2 gas. Make sure you get CO2 gas and not CO gas. But that's 393.509. 509. Now, when we go to water, that's going to be under hydrogen. Make sure you get H2O gas and not H2O liquid. So that's negative 241.818. And then probably at the very end, it's going to have the, oh God, did I seriously not? That's going to be problematic. So either things have changed or that's carbonic acid, carbonate, acetic acid, acetate. So we're going to leave off but there's other sources. If you go to the Wikipedia, you could easily find the thermochemical data for water, for ethanol. And so we can solve it from there. I'll go back to .chem. I'll look that up real quick. Okay. Standard enthalpy of formation of the liquid is negative 277.38. Okay. So all I wanted to do is make sure we understand that when we calculate this, the delta H is negative 393.509 times 2 plus the negative 241.818 times 3 minus the products, which is negative 277.38 times 1 plus 3 times 0. You're doing that, you get your enthalpy. And 3.509 times 2 plus 241.818. So you get, like, on one side, you get negative 1512.47. The other side, 277. So 7.38. You get the delta H is equal to negative 1235. Please note, this will not match the standard enthalpy of combustion that you can look up, because standard enthalpy of combustion assumes you form water vapor or water liquid and not water vapor. So you can't just cheat that way. Okay, last couple ones. We're running out of time. We might have to finish up on Tuesday. We'll see. Enthalpy of sublimation. Yeah. We'll go ahead and stop here. We'll finish this up on Tuesday. The test is on Thursday. But once we finish up on Tuesday, we got 7A and B, 8A and B, C, and a bonus. Well, the bonus is nothing. After this, we're going to look at a few nuclear chemistry problems, just a quick reminder, and we'll just start the review. Because once we have the test, once we've done the test, it's pretty much all we have is to quickly review everything we've learned that could be on the final. Because we have to go through, okay, let's remind her what the heck is a dipole-dipole interaction. What are London dispersion forces? What is a colligative property? How did we treat this? The final will be entirely multiple choice, but it's probably going to be like 70 some odd problems with a whole lot of material. A little bit here, a little bit there, probably a lot from the acid-base stuff, but you're going to need to be able to at least look at these types of problems and go, oh, how do we even know what equation to use? How do we try to approximate? How do we try to figure out what is a reasonable answer? So we'll go ahead and stop here, as I said, and I will talk to you again on Tuesday.